Okay, ladies and gentlemen, we're going to go with the next problem today. And with the next problem, those of you in 930 class may know, but our good friend Jake has, who always added into the lectures, has given me some sound clips to use. And so just to make you feel like I'm not just talking to a random webcam in my office, we have Jake ready for us. Jake, are you ready?
Yes.
See, there we go. This is good. This is good. I have four random sound clips. My wife is hearing this for the first time, so this is exciting.
Thermodynamics is best dynamics.
Yeah, there we go, Jake. Thank you very much. So we'll be talking to Jake through this problem, and you can give me some feedback if this is terrible, or you can send in your own sound clips. That's all I care about. Let's try to make fun of this. All right. So here's the problem. A gas initially at 2.8 bar and 60 degrees Celsius is compressed to a final temperature, to a final pressure of 14 bar in an isothermal internally reversible process. Okay. What we want to do is we want to determine the heat transfer in kilojoules per kilogram of the gas if A, we're dealing with R134A, and B, we're dealing with air. Okay, so that's what we want to work with here. R134A is going to give us a set of tables. You know, that's going to be in those set of 5, water, ammonia, propane, R134A, R22, and then air is an ideal gas. So we have 2 different approaches here. They both can be considered gas in the situation. And so we're going to be talking about a piston cylinder. We're compressing a gas here. Here's our system. And if we were to draw this on a PV diagram, we would have let's talk about the R134A first. We would have a vapor dome here, and we would go down, and we would start at a temperature here of this is a 2.8 bar. Let me see. Pressure is 2.8 bar. 2.8 bar and 60 degrees Celsius. So maybe here is temperature is 60 degrees Celsius, and we are going to be isothermally working on this. And this word here drives people nuts here, isothermally. So that means we're going to be competing on this isotherm. All right. Sometimes isothermally, students start thinking that means same heat transfer, and that's not true. Isothermally, remember, iso, same, thermal, temperature. Okay, so what we're going to do here is we're going to go up to a final pressure of 14 bars. That's going to go up some distance here to 14 bars. So here we go to 14 bars, and this is going to be our state 2. So state 1 and state 2 is how this is going to go. Okay, now if we were to draw this on a TV diagram, we would have a line of constant pressure, but we might be out here and saying, well, we're at 60 degrees Celsius, and so we're going to be going between 2 pressures. So we're going to have to go up to a lower pressure here. This is going to be our 2.8 bar, and this is going to be our 14 bars. And we are going to be traveling from this point to this point here, or actually the other way around. This is point 1, this is point 2. So it's still important for us in the 6th chapter. We need to have those PV-TV diagrams worked out, because sometimes they can help us with finding out what our values are, or just kind of a little bit about our process and knowing what's happening here. Okay, we're trying to find out here it says determine the work in heat transfer. I just said determine the heat transfer. I want to determine the work and the heat transfer. The work and the heat transfer here. And so we know that there is going to be some compression. So all of a sudden our work is going to be a negative work. We have to. That should be popping up into our mind right away when we see that problem statement. So a lot of things we know, we haven't even started doing a calculation yet. So let's start with here for the R134A. Okay, and we have two states, state 1, and we have state 2. Okay, and if we look up this, we're going to look up the internal energy of 1, which is going to be at well, let's write out here what our temperature is. It's going to be a temperature 1 is equal to 60 degrees Celsius, and our pressure at 1 is equal to 2.8 bar. And our state 2 is going to be of temperature 2, which is equal to 60 degrees Celsius, and our pressure 2 is equal to 14 bar. And we go to our tables, and like I said, I'd love to pull the tables right now so that you can see those, but I think it's something that you're comfortable doing. If you want to pause right now and go look these values up, we're going to look up values for internal energy and entropy here. So internal energy 1, entropy 1, internal energy 2, entropy 2. And so the values I found from the tables are 277.23 kilojoules per kilogram, and the entropy at 1 is 1.1079 kilojoules per kilogram Kelvin. U2 is equal to 262.17 kilojoules per kilogram, and S2 is equal to 0.9297 kilojoules per kilogram. Okay, that's our values there. Now, we're dealing with a closed system, and so we're trying to find out how much of the work and the heat transfer. We have to remember the first law for thermodynamics still applies, and the second law is applied. So we have to now use both of these laws here. So we're going to have the first law, delta U is equal to Q minus W. Notice I've already gotten rid of kinetic and potential energy effects because nothing was given to us in the problem statement about that. I've already assumed that. And we're going to have that the change in entropy is going to be equal to the summation of the heat transfer over the temperature plus sigma. So those two equations are going to be applying here, and we can go look into a problem statement and say that they said this is an isothermal, which we don't do anything with our equations, but it said internally reversible process. So internally reversible means that this goes to 0. This goes to 0. And so now we have, to simplify these two equations, we're going to have mass times U2 minus U1 is equal to Q minus W, and then mass times S2 minus S1 is equal to, there's only one heat transfer that's going to happen here, so it's going to be heat transfer over the temperature. Okay, and so remember also this other thing that was important in the problem statement. It said they want us to find this in kilojoules per kilogram. Determine the work and heat transfer in kilojoules per kilogram. What they're meaning is find it per unit mass. Okay, per unit mass. So we're going to divide through by the unit mass here, and we're going to get our equations to be U2 minus U1 is equal to Q over M minus W over M, and S2 minus S1 is equal to Q over M over temperature. Okay, so this here is going to have units, the same units as our internal energy has. So everything will work out unit-wise is fine with what we're going to be doing here. Now, I want to figure out the work and the heat transfer. Now, in this first equation, I have two unknowns. And in the second equation, I only have one unknown. So I'm going to go with the second law, absolutely, to start off with. And so we're going to start that, and we're going to solve for the heat transfer over the mass is going to be equal to the temperature times S2 minus S1. So this is where it's convenient that it's isothermal. It's isothermal here, so we are going to go with this. Okay, and we have to remember something for our temperature here. What do we do? Do we use what do I say? Do we use regular temperatures, or do we use absolute temperatures? Do we use degree Celsius, or do we use degree Kelvin? And actually, we shouldn't say degree Kelvin. Do we use Kelvin? So do we use degrees Celsius?
No.
No, thank you, Joe. Joe. Your name is Jake. Sorry, Jake. No, we don't use degrees Celsius. We use Kelvin. I don't know if this is going to work, Jake, but thank you for trying. It's a valiant attempt. Okay, so we're going to say here the temperature is going to be equal to 60 plus 273 Kelvin, and then we're going to look to do our S2 minus S1, which is going to give us 0.9297 minus 1.1079 kilojoules per kilogram Kelvin. And what is the answer that we get from that calculation?
Is the answer 12?
No, Jake, the answer is not 12. The answer happens to be minus 59.34 kilojoules per kilogram. But it was a great attempt. I appreciate you speaking up and asking, standing out and giving your answer there. So this is our heat transfer, negative 59.34. What does that mean? That means that heat is leaving the system, negative, leaving the system. Okay? All right, now, we now can use that value into the first equation. U2 minus U1 is equal to Q over M minus W over M. And now we know what internal energy 2 and internal energy 1 is. So this is going to be 262.17 minus 277.23 kilojoules per kilogram is equal to minus 59.34 kilojoules per kilogram. And we have minus our work per mass. And so now we're going to solve for that work per mass. And when we do that, we can get that this answer is equal to negative 44.28 kilojoules per kilogram. It's a negative value, which is what we're expecting. We are compressing that R134A, so the surroundings are working on the system, creating a negative amount of work. Okay? That's how you would do these things, the table lookups that you have for R134A. All right? Standard process that we can do and follow along. Now, we're going to do the same thing if our gas happens to be, in state B, happens to be air. Now, air, we're going to have a different PV and TV diagram. Okay, the PV diagram is going to look like this. We're going to have an isotherm here. It's at 60 degrees Celsius, or whatever we have here, 60 plus 273 Kelvin. And we're going to go from state 1 to state 2. And so we're going from a pressure here of what it was at 2.8 to a pressure up here that is 14. And then on our TV diagram, what we're going to have is two lines of constant pressure. Here's going to be our line of 2.8 and our line of 14. And we are going to have a constant temperature here of 60 degrees Celsius. And we're going to go across here, and we're going to say that we're going to go this way, 1 to process 2. So no vapor dome that we have to deal with there, but that is what we're dealing with when we're trying to find these answers. Okay, now in this problem we're going to have the same situation that we're going to be dealing with. The same two equations. It's going to come down to that internal energy 2 minus internal energy 1 is equal to the heat transfer over mass minus the work over mass. And S2 minus S1 is equal to Q over mass times temperature. Okay, so now if I want to find out what the heat transfer over mass is going to be, I'm going to go through here and I'm going to go that temperature times S2 degree minus S1 degree minus R natural log of P2 over P1. Okay, so I have to remember S2 minus S1. Now for air, I can't just look up the entry values in the tables. I now have to look up that S degree, and that's the important change here. And that's going to equal into what is our Q over mass is going to be. It still should be negative. Okay. Now for our U2 minus U1, what we're looking at, Q over mass minus W over mass, there's something that unique that happens in this problem. And I'm going to give you a second to think. What is that unique thing that's going to occur here? And the key here is that it's isothermal. And so since it's isothermal, I know that ideal gases, you look up internal energies via the temperature. And so they're going to have the same internal energies. So U2 minus U1 is going to cancel. And so for this problem, when you're looking at this problem, because of the nature of the substance we're dealing with, the internal energies go away. Your heat transfer is going to equal your work. So all we really have to do is calculate this equation to find out, and that's what I'm going to give you as your top hat question. Okay?
Is the answer 12?
No, the answer is not 12, Jake, but I'm sure somebody out there will make it 12 and try to get some points for that. It's going to be a little bit larger than 12, and you know it's going to have that negative sign on it to make sure. And so when you put the answer in the top hat, make sure you put the negative sign and the answer that you're looking for in this question. We'll go ahead and stop here, and then we'll go to another question in just a bit. As I open my thing, and by the way, thank you, Jake, for everything that you've done here for the class. I'll end it here. And if this just gets wild reviews, and it's just wonderful, we'll continue throughout the rest of it. But it might be just annoying as all hell to everybody, so I'm going to stop right there. And I had fun with it because I'm in this room. Melissa left twice during my lecture, just like a normal situation here. We'll get out of here.